Chapter 10, Section 5. We're just getting a little more complicated with the radical terms. We're going to have additions and some other stuff, products of two or more radical terms, and rationalizing again denominators and numerators with two terms and terms with differing indices. And I think we're really they're going to show us some things, especially in this part of this lesson, about how fractional exponents can be a lot easier to work with. And but we'll run into these radicals a lot, so it's very important to get comfortable with the radicals. Again, rationalization is to change it into a rational number. So if I have like the square root of 2 over 2 and I need to rationalize the numerator, I need to make the numerator a rational number, so I have to get rid of that square root of 2 somehow, which he talked about in last lesson, which would be to multiply it by the fraction of a square root of 2 over 2, which is 1. And so there's a strategy, and we have all the rules, and hopefully that it shouldn't be ever, I think at this time, if we're having trouble with the distributive property or what factoring means, those kinds of things, if that makes you uncomfortable, it's definitely time to review. Well, let's look at this adding and subtracting radical expressions. And they're going to talk about something like radicals, which are kind of like terms when we're talking about all this stuff, which I think is kind of funny, because reality what we're doing is finding a common factor, and this common factor is either the radical, or when we were talking about polynomials, they were the variable portions, right? So when we have the 6 square roots of 7 plus 4 square roots of 7, we can use the distributive property and factor out of each one of these terms here, because these are two things I cannot add because I have a multiplication here, right? So order of operations means you can't do this addition. Well, we can use laws to override order of operations, which would be in this case the distributive law, and there's a common factor of a square root of 7 for both of these add-ins here, or terms, parts that are added together. Well, they factor out the square root of 7. We end up with 6 plus 4 times the square root of 7, which we can simplify to be 10. So we get 10 square roots of 7. Very similar to adding like terms, right? Well, this is a little more complicated here when we have 6 fifth root of 4x and 3 fifth root of 4x minus the third root of 4x. Well, we need to recognize that the index of this radical is important, just like the exponent of a variable would be important. And in reality, again, aren't these just exponents? This is 4x to the 1/5 power, 1 over 5 power. Well, we recognize that I can take this group and group these two together using the associative property, and then use the distributive property, and I can say this is the same as 6 plus 3 all times the fifth root of 4x. And they end up with 9 times the fifth root of 4x minus this third root, or the cube root of 4x. So make sure that your exponents are right here, or your radical indexes. And they basically are showing that it can happen with subtraction. I'm not going to go through that, which a lot of times, maybe not in this case, but a lot of times it's a good idea to take subtractions and turn them into additions, and then I can use all my properties. I can use the commutative, I can change order, associative, I can change grouping if it's all addition, and the distributive works over addition and subtraction. But so they're basically showing that we have subtraction issues here, and notice that these are all like radicals in a sense. So I have 1 cube root of 2 minus 7x cube roots of 2 and 5 cube roots of 2. Well, we can basically take the coefficients, if we want to go back to this like term stuff, and add those together, and we get 1 plus a negative 7x plus 5, or 6 minus 7x if you want to keep that subtraction. And also you got to remember these parentheses are important. To go back to the originals, we'd have to distribute that multiplication of the cube root of 2 over each part of this, which would be simpler, but it would be the same as saying, well, let's take this one and this one, because I can actually do 1 plus 5 and get 6, right? A little more complicated here. Notice that what they do here is they're looking for common terms. So I have the cube root of 2y here, but I have the cube root of just not 2y. But I can factor that. I can factor out a cube root of 2y out of this expression here. And then using my product rules, I can say, well, that's the cube root of x to the 6th y cubed all to times, the cube root of 2y. Why did they do that? Well, that matches with this cube root here of 2y. So we can basically add those two things together now and get 8 times that, right? Or excuse me, we end up with a grouping and we factor out again, which would be x squared y plus 7, right? I didn't say that right to begin with. But so we look for opportunities to simplify or get him into another factors, really, and it is a process of factoring. So like when we're going through, a lot of times the reasons to factor is if we end up with fractions, or we get products of these things with different exponents. A lot of times the only way we can do that is to get factors and then try to get that equal to 0, and then we might be able to find some solutions to equations that way. Well, here we have products of 2 or more radical terms. And this is going to come into reminding us a lot about factoring of polynomials, right? So if I have a here, this square root of 3 times the quantity x minus the square root of 5, I can use the distributive property, and I end up with the square root of 3 times x, or usually they have the thing outside. Just they put that up in front, I think mostly so you don't get confused about where that top line will end. So it's x square root of 3 minus the square root of 15. Okay, remember the product rules again. In this case, we can distribute the cube root over these things, and they simplify. They're using a lot of the stuff we've covered in prior sections. But here's something we haven't seen for a little bit, but is the square of a binomial. What does that really mean? And if you remember how to do this, which is the first term squared, the last term squared, and 4 times this term doubled, right? So you get 4, or negative 4 square roots of 7, and you double that and you get a negative 8. Which is a good thing to remember, especially when we're trying to see this type of polynomial, maybe, and factor that. Though, I don't know why we would, because this is sure possibly a better way to do it, to show us something. And in reality, this is equal to a specific number. We can't express it accurately because it's a rational number, but it is a number. And this is probably the simplest way to accurately show us that number, right? So then this square root of 7, depending on what the application is or how we ran into this, like we talk about, if I'm talking about some equation which involved when I'm walking downtown Wenatchee or something, I'm probably not going to need the square root of 7 to be very accurate. But if I'm talking about trying to get some kind of payload through space to Mars, it's a pretty big deal about how accurate we go with the square root of 7. Here's that FOIL stuff again. And that's the only thing we can do in this case. There's no shortcuts for two different binomials. So here's FOIL, which stands for first times first. So 4 square roots of 3 times the square root of 3, and we'd end up with 4 times 3. Remember that you square the square root of 3, you'll get 3. The O portion is outer times outer. We get 4 square roots of 3 times a negative 5 square roots of 2, and we end up with a negative 20 square roots of 6. Inner is square root of 2 times square root of 6, get the square root of 6, and last is last times last here, square root of 2 times a negative 5 square roots of 2, and you'll get a negative 10. Simplify what we can. Well, I can add the 12 and a negative 10 together. Negative 20 square roots of 6 plus 1 square root of 6 is a negative 19, and so on. So we're running into a lot of stuff from prior chapters about how do we multiply these binomials in a sense, though they actually probably are numbers in this case. And then they just basically go through this with variables underneath the radical. But hopefully you recognize this one. This is a good reminder. This is difference of squares. Something plus something times something minus something ends up being the first term squared minus the second term squared. So you end up with a minus b. I'd sure rather remember that and go to that right away. And this is probably a good example why they time test a lot of times, is they're going to give you a problem like this and say, I wonder if they remember that this is difference of squares. Or you could do FOIL, which takes longer, and you end up eliminating that middle term. The outer and inner term goes to 0. Well, rationalizing denominators and numerators with two terms is, again, what that means is I need to convert it into a rational number, which is a fraction that can be represented with two integers. Well, square root of 3 is not rational. That's a real number, but it's an irrational number. I cannot express that as a fraction of two integers. So they want us to write the equivalent expression with a rational denominator. So in this case, we have this something plus something. And I need this square root of 3 to go away, or to be squared in some way. Now, I just can't square both these and say it's going to be something. I need the rules to work for the distributive property. So when I multiply anything, like if I took this times square root of 3, I'd have to take 7 times square root of 3, and I still have the same issue, is that this will go to 3, but then I got 7 square roots of 3. So I didn't rationalize that denominator. What I need to use is the difference of squares. If I take 7 plus the square root of 3 right here, and I took that times 7 minus the square root of 3, I have a difference of squares scenario here, and a strategy that I use. But also, if I want to do anything to a fraction and not change the value, I also have to remember I'm multiplying by 1. 7 minus the square root of 3 over 7 minus square root of 3, that's equal to 1. So I'm not changing the value. Well, when I do this multiplication in the denominator, that's the difference of squares. That gives me 7 squared, the first term squared, minus the second term squared, which ends up being so that I do not have a radical in my denominator anymore. So I end up with 49 minus 3, which is 46. And then I also have to distribute this 4 times this 7 minus the square root of 3. Very easy error would be to do all this complicated stuff figure out what I need to multiply, and then take 4 times 7 and forget to distribute it to the square root of it, a negative square root of 3. So don't forget the easy parts. Distribute that and you get 28 minus 4 square roots of 3, all over 46. Now I'm not done because there is a common factor. When I see this, this is even and this is an even times it, right? So I have an even number, or a 2 could be a common factor. And that's what they do, is that they say, hey, this, I have 2, at least 2 as a common factor. So they factor 2 out of this, and I get 2 times the quantity 14 minus 2 square roots of 3. And 46 would be 2 times 23. So, and then that ends up to be 1, doesn't it? I can rewrite this fraction as 2 over 2 times this, which is 1 times this, and you get that. So difference of squares is really handy when we have these kinds of things. Very useful tool, and we can apply that as a strategy to rationalize or convert from radical to rational number. Now in this case, make sure you read this. It says rationalize the numerator in this case. So in the numerator I have 4 plus the square root of 2. I'm going to multiply by 4 minus the square root of 2, and I get that difference of square scenario again. Make sure you're going to multiply by 1. Very easy. When I look at students' works, a lot of time you tend to skip this portion here, or you have some kind of shortcut that you're trying to look for when you're multiplying or dealing with fractions, and a lot of that comes from probably memorized techniques that you've used when we've just had fractions. I would really write this out all the time just to make sure you don't forget something. Well, in this case, this is the difference of squares on the numerator, so I get 4 squared, or 16 minus the square root of 2 squared, which is 2. So you get 14 on top. Now I need to distribute this still on here, which I end up with first times first is 4 square roots of 5. Outer times outer is the square root of 10, and it's negative. Inner times inner is a negative 4 square roots of 2, and square root of 2 times square root of 2 is the last times last, you get 2. Now I look for things that I could simplify, and in this case there's not anything. Now they're talking about concepts here. If we have, this is a nice summary of what we've gone through in the example so far. If I have one term, I can multiply by that radical, usually that's in the denominator or the part that I'm trying to rationalize. If I have 2 terms, you need to remember that I can multiply by 1. In fact, that's what's going on with both of these. I can multiply by 1 using a conjugate of the denominator, or in other words, the second part of that difference of squares. Okay, let's look at terms with differing indices, which is have different nth roots, right? So let's look at example 7 here. I have the 4th root of x plus 3, the quantity to the 3rd power, all over the square root of x plus y. Well, now they bring out the exponents. They're going to say, well, in reality, and we've covered this, we can convert this radical into an exponent. In fact, this index here is the denominator of the fraction. So I would have the 3 power to do that. But really what you're doing is, if this is the 1/4 power of this whole thing, you take power of power, you multiply 1/4 times 3, and you get 3/4. Here is the square root, so there's really a 2 there. So I have x plus y to the 1/2 power. Now the rule of exponents, when we have a like base, this base and this base, the part that has the exponents, when I use division I subtract the exponents, which is 3/4 minus 1/2, and you end up with 1/4, right? So remember, here's that fraction manipulation that we're doing when we're trying to rationalize, right? How do you change 1/2 into fourths? Well, I take it times 2 over 2 and I get 2 over 4, which is the same as 1/2. Same process we've been working with fractions for forever. Still works in these algebraic expressions that are just more complex, not really more complicated. We're applying the same rules with strategy, right? So, and here's a strategy box. To simplify products or quotients with differing indices, convert all the radical expressions to exponential notation or turn them into exponents, right? When the bases are identical, subtract the exponents to divide and add exponents to multiply. This may require finding a common denominator for the exponents. This part right here they're talking about. Convert back to radical notation and, if possible, simplify. And I'd probably simplify before I start bringing in radicals again. Okay? Now, as far as these lessons go and stuff, follow the directions. They want us to convert back to radical notation. Make sure you do that. A lot of times you'll find out that in algebra it will be okay to leave things in their exponential form when you get to a point where you should be comfortable with fractional exponents. Well, let's look at this one here. We want to multiply the square root of x cubed times the cube root of x. Well, that's the same as x to the 3/2 power, which is, this index is 2, right? So I get 3 over 2, 1/2 times 3, which is 3/2. And here I have the cube root of x to the 1 power, which is 1/3 times 1 is 1/3. I'm multiplying, these bases are the same, so I can add the exponents. I get 3/2 plus 1/3 is 11/6. So what does that mean in going the other way? The fraction is the denominator is your index, and this is your power when you put it in this form. So this is a 6th root of x to the 11th power. Now, we can simplify that. In fact, I'm pretty sure the book's going to show us this too. But I could look at this and say that 11/6 is really 1 and 5/6, right? Which means that I have x to the 1 times x to the 5/6 power right here. X to the 1 power. This is really x to the 5/6. So I convert this to a mixed number, which is an addition, right? And then I can convert it back too. So, and I'm pretty sure hopefully they'll show that too. But I wouldn't convert to radical here. I would simplify this expression here based on the exponent, even though it's fractional. Example 9, they give us a function here, and they have two functions. Again, this is function notation. We have f of x equals the cube root of x squared, and g of x equals the square root of x plus the 4th root of x. And they want to find out, when I multiply these functions together, what is my result? Or find f times g of x. Okay. Now we recall that f times g of x is the same as f of x times g of x. In other words, this, the cube root of x squared, times this. Remember, we need to distribute. Well, they converted all these to exponents, which is a very good plan. In fact, some of the prior stuff, I would say. This is something you can do all the time with radicals, is what I'm trying to say. So if you start applying this earlier, I think that's a good idea. You're going to make less mistakes, but make sure you answer the question the way they want it answered, which in this case they want us to put it back in radicals. Well, we end up with this multiplication we need to distribute. Well, before they do that, they convert it to exponents. So the cube root of x squared is x to the 2/3 power. The square root of x is x to the 1/2 plus this fourth root, which is x to the 1/4 power. Well, when you distribute, you take this times each part of those addition, and so we end up with x to the 2/3 times x to the 1/2 power, which our powers rules is we can just add those exponents, add these exponents because the bases are the same. So we add those, we get 7, 6, and 11/12. Okay. Now, you can't, we have no rule about exponents when we're adding bases of different exponents and all that kind of stuff. They're not like terms. We have a lot of limitations there. Don't make the mistake they think you can just start adding exponents there. They have to be multiplied together to add those exponents. Well, then they convert it back to radicals. I would skip this step and really say x to the 7/6 is x to the 1 plus 1/6, which is x to the 1 power, x to the 1/6 power is the 6th root. This one is 11/12. Well, I don't have any way to bring anything out of that. There's no mixed number that's a proper fraction, or I can't make an addition out of this. It's going to make it any simpler. So you get the 12th root of x to the 11th power. Example 10 is just dealing with division now. So we convert these radicals to exponents, and if we have like bases, and in this case you think, well, maybe not, but I can distribute this 1/3 power over these exponents because it's a power of a power. So this really ends up to be a to the 2/3 power, b to the 4/3 power. Hey, guess what? Now I have like bases. Here's an a and here's an a, here's a b and a b. Now the division part of that is I write that as a subtraction of these exponents, so this a base is going to end up going to the exponent 2 to the 3rds minus 1/2, and the base b here for this variable b is 4/3 minus 1/2. Well, do the math and you get a to the 1/6 power times b to the 5/6 power. There's nothing I have no mixed numbers here. I can't take out full roots in a sense, is another reference back to some prior terms, right? But I still may be able to simplify or write it as a different thing. So what we do is we end up, they're both 6th root. So we have the 6th root of a times the 6th root of b, right? And I can see where this is a good example of where maybe going back to radicals could remind you how you should write this. Well, when we have the same index, we can put it all under that index, or under that 6th root in this case, and say it's a times b to the 5th. Okay? And they call that using the product rule of radicals. And that's, that's true, right? So I could go through another way, but we'll wait for that. Okay? Well, that brings us to lesson or exercise 5. I think there's 8 sections in this chapter. We'll get through this in the next few days, and good luck on the assignment.